Hello, everyone. My name is Supranta, and I'm a postdoc at the University of Pennsylvania. In this talk, I'm going to be talking about some of our recent work on trying to build a field-level inference pipeline to analyze weak lensing data. This is work done in collaboration with all the people who are listed here, and some of our recent work can be found on the archive number that are listed here.
Okay, let us begin by reviewing the usual approach that we take to constrain cosmological parameters from weak lensing data. So usually, once we're given a catalog of galaxy shapes that
telescopes such as Dark Energy Survey or in the future LSST will measure, we take the catalog, we take these galaxy shape catalogs and compress it into a handful of summary statistics, usually what are known as correlation functions. And we have a physics model that predicts what these correlation functions should look like as a function of different cosmological parameters. And by comparing the theoretical predictions to the measurements, we can put constraints on different cosmological parameters. However, two-point functions are suboptimal. To understand this, let's just look at the plot that's shown below. The two maps that are shown here have the exact same power spectrum, but the map on the right is a Gaussian random field created by scrambling the phases of the left-hand side. As we can see, in the Gaussian random field, we don't see features such as filaments or dense clusters of galaxies that is otherwise visible in the n-body simulation map. What that indicates is that there's additional information in the n-body simulation map that we miss if we are only looking at the two-point function. So to extract all the information that's there in a dark matter map, what we propose is to use what are known as field-based inference methods. In this method, we avoid compressing the data from the galaxy catalogs into correlation functions. And instead, we try to extract all the information that's there in the full map. And the philosophy behind this is that if we know the underlying map, then automatically we know all the summary statistics that's there in the data. Therefore, it's a principled way to optimally extract all the information that we can find from a given data set. So the way field level inference works is something like the following. So we start off by imposing some prior on the field that we're interested in. For example, the density field, the underlying density field that we want to infer. And then we forward model the observations that we can paint on these density fields, for example, galaxy shapes from a weak lensing survey. And then we compare what we observe from the telescope at the field level. And depending on how good a match the forward modeled observations are to the data, we change the field which was used to create these observations. And then by doing this over and over, we get a density field that actually fits the observations from the telescopes. So for weak lensing, the way that the way this would work is something like the following. Here, the yellow ovals indicate galaxy shapes, and by looking the galaxy shapes on the map, we want to forward model the underlying density field that has created that particular shape distortions. So we start off with some random density field, and we look how well the observed shear map looks compared to what we are forward modeling. And then the main trick here is that we treat the density field or the convergence field on each pixel as parameters that we want to infer, in which case we can turn this into a Bayesian inference problem of inferring the map given the data. And we run an MCMC chain where, which is a very high dimensional inference, but it can be done by using gradient-based sampling schemes such as Hamiltonian Monte Carlo. And once we do this, in the end, initially you see that, these fields are, trying to fit the data and, just burning in. But once it's burnt in, it explores all the possible maps that could have generated the observed data that we see. So we developed a code called Karma that does precisely this. you can find the code here on this URL, on this GitHub repository, and you can use that to run Karma yourself. So what Karma does is it tries to do this sort of a forward model on the full sky, on the full sky using Helpix maps, and also includes the tomographic cross correlations between different maps. And in Karma, we assume that the convergence field can be well described as a log normal field. This log normal model has been widely used in cosmology to model the convergence field. So here in this plot is a comparison of the log normal model to the convergence field from an n-body simulation. And as you can see, at all resolutions higher than 10 arc minutes, the log normal model actually fits the 1-point function of the convergence field very well. So in other words, the log normal prior gives us a analytical way to describe the convergence field that fits both the 2-point function and the 1-point function very well. And in addition to that, so because it models the 1-point function correctly, we also get non-Gaussianity in our field. So we used Karma to create mass maps from dark energy survey year 3 data. Here I'm showing one of those examples. On the top left is the map that we create from Karma, and the other maps show the publicly available maps, mass maps that were created using other methods. So as you can see, Karma produces a map where we start resolving smaller structures than other methods. The most useful comparison here, or like in terms of methods, the methods Karma is closest to the Wiener filtered map. And as you can see here, by looking on the top left, the Karma map starts resolving smaller structures than the Wiener filter maps. That is because we also consider cross correlations in our maps, which Wiener filter maps as created by the dark energy survey ignored. But more importantly, the maps we create also have the correct 2-point function, which is not trivial. And in fact, here in the black points, I show the measured 2-point functions. On the top right are the pseudo-CLs, and on the bottom left are the correlation function, the 2-point correlation functions. And most mass mapping methods that we currently use, like Wiener filter or Kaiser-Squires method, they do not have the correct 2-point function. But as you can see, the Karma maps, which is shown in blue, actually passes through all the measured 2-point function data that's shown in black. However, like despite its success of reproducing the correct 2-point function, there are some issues with Karma maps that we show here. Specifically, if you look closely by looking at the 2-point function, there is a slight bias in the recovered power spectrum. And this magnitude is something of the order of, say, 5% in the power spectrum. And that's because, in spite of the success of the log normal model, like, in detail, if you look closely, the log normal model fails, as shown as shown in the figure on the right. Now, this bias that we see is not significant for the current surveys. So for something like DES year 3, if you look at the chi-square distribution of a bunch of 2-point function as well as some of these non-Gaussian summary statistics, you get the exact same chi-squared no matter what. So what this is saying is, even though we have this bias is not significant once you add the noise at the noise level of the current surveys. However, once we get to the next generation surveys like LSST, the log normal model will not be sufficient. So we do need to improve our forward model that we use for our field level inference. And this is related to a broader problem in weak lensing cosmology today. So any simulation method that we can devise usually has a trade-off between speed and accuracy. So approximate methods such as log normal simulations that we talked about are usually fast, but they lack in accuracy. And to get more accurate simulations, we need to run a full n-body simulation and then do ray tracing simulations to get accurate weak lensing simulations. And in general, any method that we can come up with usually lives in this part of the space of speed and accuracy. But for stage 4 surveys, we will need many accurate simulations. In other words, we need to get to this part of the speed and accuracy space. And the question is, how do we get there? Now, we already saw that the log normal model actually does pretty decent. For the current stage, for the current surveys, the log normal model actually describes all the 2-point and the non-Gaussian summary statistics very well. So what this suggests is that we only need to make small changes to the log normal model to get high quality weak lensing maps. And this is the sort of work for which machine learning methods are very well suited, where we can feed in a log normal model to a machine learning black box model that can turn it into another map which looks very close to a real weak lensing simulation. And this is precisely what we tried doing in another paper of ours. And for this, we used the machine learning method called generative adversarial networks, or GANs for short. So what GANs does is that it sets up the training as competition between two neural networks labeled as G and D. So the G, which stands for the generator, takes a random noise variable, which is shown by the Z here, and then converts it into a map that it wants to generate. And then the task of the discriminator is to discriminate between that generated map and a real simulation map that you can feed into the discriminator. And when you set up the training as a competition between generator and the discriminator, at each iteration, the generator starts getting better and better. And the discriminator then finds it difficult to distinguish between a well-generated map and a real weak lensing map. So in the end of the training, the generator ends up producing mask maps which are exactly similar to the simulation maps that are fed into the discriminator. Now, usually when people train GANs, the latent space that is used is a low-dimensional normal or a uniform distribution. But one change that we make in our method is that it doesn't have to be a low-dimensional space, but we can have the latent space, which are essentially maps drawn from a log normal random distribution with the same power spectrum that we want to generate. And in that case, the generator only needs to do small changes to the log normal map to create simulation maps that are very close to the real maps. And by doing so, we can achieve this sort of a training with very small number of neural network parameters. We only need around 1,000 parameters to get good simulation quality maps from the log normal maps. And another useful thing about our method is that our method directly produces curved sky, heel pix maps with the GAN. Another important thing about our method is that our method is not just a black box machine learning algorithm. You can actually explain what our algorithm is doing. For example, in this plot on the top panels, I show the input to the GAN, and on the bottom we show the output. So first of all, you can see that the output actually preserves the same features of the input log normal maps as you can expect. But now you can zoom in and see what exactly is the machine doing. For example, if you look at these peaks on the second panel, you see that what the GAN is actually doing is that it's taking a peak in the log normal map and actually making it more compact. Similarly, if you zoom into this other peak on the extreme right panel, you see that what it is doing is it's taking one peak from the log normal map and then splitting it up into multiple smaller peaks. The explainability of the method is very desirable for scientific applications of machine learning. Next, by looking at different non-Gaussian summary statistics, such as the PDF, peak counts, and the void counts, we see that while the log normal cannot reproduce these statistics, the GAN has the same summary statistics as the simulations. So the GAN summary statistics are shown by the red dashed line, whereas the simulations are shown by the blue solid line. And as you can see, both of them look very alike. And even more concretely, if you want to see the chi-square distribution of different summary statistics, we see that the GAN reproduces the same chi-square distribution as the simulations, whereas the log normal does not. This is suggesting that we can use this GAN to run fast simulation to compute covariances of different non-Gaussian summary statistics. Now, the PDF peaks and the voids are in some sense local in the sense that they're pixel by pixel. But we can look at other non-Gaussian summary statistics, such as bispectra, which looks at the non-Gaussian Ts, which are separated by some scale. And we see that the GAN sky, again, gets the same bispectrum as the simulation where the log normal model fails. And not only that, like it also captures the non-Gaussian T between different redshift bins, or in some ways like the cross bispectra, as shown in the plot below. Okay, so far I've not talked about cosmological inference at all, but it is easy to extend our field-based map sampling method to also sample cosmological parameters using a two-step sampling process, where in the first step, we sample the maps given the cosmological parameters, and in the second step, we sample cosmological parameters given the maps. And we showed that this process gives us the correct posterior for a simple analytical case where we can analytically marginalize out the maps. In the red contours shown here is the analytical case where we have marginalized out the maps, and we're just sampling two cosmological parameters. And posterior from the field-based inference is shown in black, where we're inferring 300,000 parameters. And we show that both these contours look very similar, showing that the field-based inference gives the correct cosmological posterior. And with this pipeline, we forecasted the gain in cosmological information from field-based inference, and we saw that for an LSST year 1-like survey, we will get up to 2.5 times stronger constraints on dark energy equation of state using field-based inference. However, if we do a similar analysis for lambda CDM, we do not find significant gain in S8 parameter, but we do see some degeneracy breaking between omega m and sigma 8. With that, I'll end my talk, and I'm looking forward to interacting with you all in a week's time. Thank you.